Okay. Good afternoon, everyone. I hope everyone is doing well. We're the student team Geotek from Monash University. I'm today's presenter, Yuxi. We would like to express our gratitude to the ARMA and all the organizers and sponsors for organizing this great student design competition for us. And today we're going to bring you a presentation about near-field tunnel design. So first of all, what is exactly our project? So from the engineering aspect, it is a 3-meter radius circular tunnel adjacent to 1-fold or 2-fold scenarios. The tunnel sits in a rock mass environment with varied rock mass property. The water table is almost at ground surface, but is barriered by the fold 1 here. The lateral earth pressure ratio, which is the ratio of the horizontal stress to the vertical stress, is 0.4 to 0.6. The project is aimed to find the minimum and optimum tunnel depth under the engineering construction. In the meantime, there are 2 scientific challenges contained in this project. One of them is how to quantify the probability of the slip. So the Monte Carlo method and point estimate method as the 2 statistical methods are used in this project. And another challenge is about how to define and achieve the factor of safety. It is defined as the load carrying capacity of a system beyond what the system actually supports. And it is achieved by using the strength reduction method. The result of FOS could be driven by either the point velocity, displacement, or the stress. Those scientific problems will be further discussed in the following slide. But now I would like to provide you a general view of our project in this page. So first of all, we start from building the model geometries and building in the key mechanical properties by the Mohr-column constituting model. Next, the probabilities of the slip and the factor of safety can be calculated. The figure in the middle left shows the POS. The red curve shows the cumulative function of fault slip state. The red area indicates the cases in fault slipping state, and the area in blue indicates the stable fault cases. The contour of FOS shows the areas in red has a low FOS value, which means a comparatively unstable state than other areas. We take both 2 stable index to check if they meet the requirements or not. And if not, we will go back to the initial modeling state, changing the input parameters till we find the optimum design. Okay, now let's take a closer look at the numerical modeling part. The model is sized 6 meters times 40 meters, taking the Mohr-column as the constituting model, where the cohesion, friction angle, and tension strength are the key controlling variables. When we talk about the variability of the rock mass and fault properties, we introduce COV, the coefficient of variance. This is defined as the standard deviation over the mean value, and by setting up the COV, we could take the parameters normally distributed into the model. The input parameters can also be seen in this table with the COV values shown in the bracelet here. Besides, the model also set with a linear gradient horizontal stresses with the Earth's lateral pressure ratio from 0.4 to 0.6. And we consider the overburden pressure with overburden depth 40 meters at the top of the model as well. It is noticeable that the interface model is selected for fault simulation, and the semi-tight joint thicknesses are selected based on the provided rock quality. The friction angle of the fault is also set in normal distributed by the COV values shown in the table here. Okay, before we take any further, there are some adjustments we would like to raise about. So for the consideration of COV, the Flex 3D has the COV function for variability simulation. However, the assigned value could be negative if we've got large COV value, as the example of the cohesion figure showing in here. And the function is unavailable for the interface model either. Therefore, we take assistance from the Python console of the Flex 3D to generate the parameters in normal distribution and use Python API of Flex 3D for material property assignment. Moreover, there are some modeling scenarios applied to the model. The 4-phase excavation method is used into the model, and the excavation length is taken as 1 meter in the unsupported condition. From the figure here, we compare the displacement in the 1 meter excavation length with the 60 meters excavation length. And the case with 1 meter efficient length has a smaller displacement result compared to the other cases. For the calculation efficiency of the large calculation cases, we choose 1 meter calculation length into the model eventually. Let's talk about the methodologies on the achievement of the probability slip, POS, and factor of safety. So first of all, let's talk about the POS. The Monte-Carlo method is used for the benefit of the higher accuracy. It works by taking the variables into the consideration, generating a large number of cases with randomly selected variables, and counting the number of cases with slip default, which is M, over the total number of cases M. To be more specific, the table shows more than 2,000 cases with randomly selected parameters in each case. Each variable follows the normal distribution with given COV, and all the 4 variables are independent from each other. It is noticeable that we choose the 4 variables here as provided from the question, but we can always bring more variables into the consideration using the same method. Moreover, the interface slip state can also be provided in the modeling as the figure showing here. It returns 0 for the non-slip state and 1 and 2 for the slip state in the red zone shown here. Okay, we use the point estimate method for the reason of less time consuming and efficient estimation. But both those 2 methods can mutually verify. So for the point estimate method, the interface slip state is determined by comparing the stress state and friction angle of the fault. As the friction Y, stress state is the value of shear stress over the normal stress. The point estimate method is targeted at obtaining a probability density function of the fault slip by inputting the 2 probability density functions. One is the normal distribution function of provided friction angle of the fault, and another is the friction function Y as we mentioned here. The figure at the bottom indicates the probability density function of C. The curve in the black is the cumulative curve. Since we wish to know the probability of the fault slip state, then the red areas of C less than 0 locates the POS values around here. Okay, now let's take a look at the FOS values here. It is calculated by using the Flex 3D FOS function with more column strength reduction method, where the parameters are reduced step by step to find the critical value of the failure, and the reduced coefficient locates the FOS. So this is the example of the cohesion and the friction angle. So the FOS is driven based on the high velocity of the grid point, as the figure on the right-hand side showing. For example, for the tunnel depth of 60 meters, the red arrays on the top of the tunnel has FOS equals to 1 and the highest grid point velocity in unstable status. Comparably, for the tunnel depth at 71 meters, the FOS is generally 2 in a stable status and much less grid point velocity. So now let's take a quick review again of our whole structure. So this time we introduced the blue box for the application of the Flex 3D and the green box for the Python application. So let's go back to the structure. Firstly, we start from the model geometries with number of faults and depth of tunnel as the 2 variables, while we consider the 4 key variables with parameter variability, the COV value features into the model. Next, there are 2 stable indexes, probability of slip and the factor of safety. Based on the slip state and the stress state, the Monte-Carlo method and point estimate method are the 2 flexible chosen methods for the POS values, while for the FOS, the high velocity of the grid point and the strength reduction method are the way to generate the FOS values. After all the above steps, we can calculate the result of POS and FOS less than 5% and larger than 1.5 respectively as required. If those stable indices can meet the requirements, then the optimal location of the tunnel can be output. Otherwise, we go back to the initial modeling state, changing the input parameters till we find the optimization design. Okay, so So from the aspect of the POS and FOS, the results are shown in this page. For the probability of the slip, the results are both shown in the table and in the figures. It is clear that from the figures, for 1/4 scenario, the POS is above 80% when depth is 61 and 62 meters, but it drops down significantly when the depth increases from 63 meters to be less than 5% of the POS. The similar result happens in the 2/4 scenario. The critical point is around 72 meters. Therefore, for the required probabilities of the slip less than 5%, the tunnel depth should be at 63 meters or deeper for 1/4 cases and 72 meters or deeper for the 2/4 cases. And the same results can also be seen in the tables to have the specific value here. Meanwhile, for the safety factor, from the bottom table, the FOS is larger than 1.5 when the tunnel depth increases from 61 meters for 1/4 scenario, and the similar results for the 2/4 scenario as well. The figure also shows that for the 6 meters tunnel depth, the low FOS value in unstable states with the large displacement in the red areas at the top of the tunnel, while for the 2/4 case at 71 meter depth, the FOS is 2 in a more stable status with a smaller displacement over here. It is noticeable that we set the FOS bracelet of Flex 3D as 1 or 2 to save the computation power. It is concluded that by comparing the result of the POS and FOS, we can tell POS is more critical than the FOS on the determination of the optimum tunnel depth design. And the 63 meters for 1/4 and 70 meters for the 2/4 by the FOS is the minimum and optimum depth of the tunnel. Now, let's quickly wrap up our result. The minimum and optimum tunnel depth are 63 meters for 1/4 scenarios and 72 meters for 2/4 scenarios. In terms of the construction method, we got road header and drilling and blasting method for partial phase excavation and TBM for the full phase excavation. However, based on our construction method, the construction sequence, the small diameter tunneling in the weak rock mass is not ideal for the partial phase excavation. Since the tunnel is adjacent to the fault, the on-time support is also highly required, but could be challenged for the road header and the drilling and blasting method. Moreover, the excavation direction is strictly required to be horizontal and keep the tunnel in the same depth, but it couldn't be guaranteed by those two methods. By contrast, the tunnel boring machine TBM method has a stable excavation performance, faster construction speed, and a small disturbance to the rock mass. Therefore, we suggest TBM with lining. The figures and table also shows the table effects brought by lining and the rock wall support. It can be seen that for the 1/4 case at 6 meter tunnel depth, the lining improves the POS from 100% of the failure fault slip to the 0% of the fault slip, and the convergence from more than 1 meter to 5.4 millimeters. And furthermore, we also provide some thought on the further optimization potential. First of all, the fault parameters and orientations are the important and influencing factors for fault behavior. However, it needs further considered in the next step. Moreover, the study and design on the advancing rate and the length should also be taken into the consideration, as we modeled in the previous slide, which shows the displacement differences on the different advancing lengths. Okay, this is the reference list. And this is all for our project presentation. Thank you all for your attention, and we would like to thank all the organizers and our supervisor, Dr. Chen Bing Chang, for the general support. Now we're happy to take any questions. Thank you.
Thank you, Team Geotek judges.
I have a question.
Yeah, go ahead.
What do you? Yeah. Can you comment on the realistic of the large change in horizontal stress over 40 inches, 40 meters, excuse me, that you put in your model?
Sure, just give me a second. This one. Oops. Okay. So this page here, right?
Yeah, how realistic do you think it is for the stress to change from 40 meters to 80 meters depth that drastically?
Okay.
Oh, okay. Can I answer the question? This is a geological condition given by the problem statement of this project, and we increase the Kn by the depth to simulate the realistic conditions, like in the real conditions, the stress normally increase with the depth. Yeah.
Okay.
So a follow-up question on that point. So you're assuming that all of the material has the same unit weight, but the material above is saturated and the material below, I guess, is unsaturated. What does that say about the porosity of those two materials?
Yeah, I think I can take this question first. So, so first of all, our all the rock materials assumed to be isotropic and homogeneous. So all the materials of the rock mass is set into the same. But as we said in the first, or setting these figures, so because the water table is around the ground surface and is barriered by the fault one, so we will set the pore pressures into these zones. So these zones will contain with the water, and we set the pore pressure over here. But for here, it is the water is buried by the full one, so we don't consider the pore pressure or any water effects in these zones.
Right, but you have the same unit weight for both materials, correct?
Yes.
So just what does that tell you about your assumption on porosity?
I may answer this question. Since we are in this problem, we only investigate the COV, the effect of the mechanical properties here. But for some other parameters like elastic modulus, densities, and we can also assign it as a normal distributed properties. But we only provide a method here. If we want to take that the other parameters into consideration, we can also add it.
Okay, thank you.
Oh, I think I can add some complication, and this the strata above the fault one, the soil and rocks, the unit weight of this rock contains the water weight, and under the fault one, there is no water formation. Yeah.
So why does your sigma, lateral stress factor vary with depth?
Sorry, can you
KH
repeat?
varies with depth. Why does it vary with depth?
Why? What?
Your KH varies with depth.
You assumed it went from 0.4 to 0.6 over those 40 meters. He's asking,
Wow.
why did you assume that?
Yeah, that one.
Firstly, the KH 0.4 and 0.6 is a given condition of this problem project, and then the KH can vary a lot due to the ensued stress, especially in a deep depths. Yeah, in rock mass, there are geological stress. Yeah.
Yeah, we just assume the 0.4 and 0.6 to be the values ranging with the depths, but we also verified like this is a very general or reasonable values in the very reasonable range.
And what's more, we have tested the effect of the KH. We tested that the KH constant with 0.04 or 0.6. It has a little effect on the final result. Actually, yeah.
Okay.
We assume that just because we want to be consistent with the given condition of this problem statement. Yeah.
Okay.
Okay, so thank you, judges.